Okay, let's get started on another ranking task. These are definitely worth your time. So if you haven't yet just spent time on your own working through them, please stop this video and go back and do that for yourself. We'll start with this first exercise, number one. In this one, it's really the identical circuit in cases A, B, and C, and they're just moving the ammeter around to see if they can fool us. And what this is for is to diagnose a misconception that's somewhat common that some students have, that current is a quantity that gets used up over a component. And so if a student is having that misconception, you can usually catch it right here. That's an important one to catch really early on because it's hard to build a working model of circuits with that misconception. We know that all the bulbs are identical and the batteries are identical to one another in here too. So we know that the current is going to be the same in all three cases there. Doesn't matter where we put the ammeter. There's only one path for the current to follow. Exercise 2 is a little bit similar here. Again, these are identical resistors, these bulbs, right? And they're wired over the exact same battery, so we can call that battery E there. The current in any one of those branches is going to be equal to the potential difference across it, which will be equal to the battery potential in these cases, because these bulbs are all wired directly to the battery, divided by the resistance of each bulb. The resistances are the same. They're each wired over the same potential difference, so the currents are going to be the same in all three cases. And again, this is probably to address a misconception that a student might have of like a bulb that's closest to the battery would somehow have the most current or something like that. So if you're having those thoughts, then just know that these exercises are designed to get rid of some of those. Circuits are the topic where students probably come in. I don't know, circuits and forces are probably for the whole year the two topics that students come in with the most misconceptions. And that makes it harder. Actually, it's harder to learn when you have a broken model than it is to learn if you don't have any model at all in your head. Okay, exercise 3. Now the ammeter, notice that the ammeter is wired in series with the battery. So essentially we are ranking the battery current in all three cases, and that's just going to rank inversely with the equivalent resistance. So battery current will be equal to the battery EMF divided by the equivalent resistance. Remember, we've done a bunch of problems like that. So equivalent resistance in case A is just R. Case B, R over 2. I've got two resistors in parallel. Case C is 2R. I've got two resistors in series. So I'm just going to rank inversely with that. The lowest resistance, of course, is going to have the greatest amount of current. So that'll be case B, then A, then C. And in the last exercise here, number 4, same thing. They're just kind of wanting to put a little extra emphasis on parallel wiring here, I think. So equivalent resistance for the first one's R, second one is R over 2, third one is R over 3. This is important to go over with students because the way our brains work, just kind of without thinking about like our reactive brains, our work on the basis of more is more. So if you see more resistors, your brain, like if you just don't think about it, will think, oh, there's more resistance in that circuit. Where actually, if they're wired in parallel, the equivalent resistance or the effective resistance with respect to the battery decreases as you add more resistors in parallel. So just notice that takes a little bit of analytical thinking. That's not an intuitive thought. Our brains don't intuitively go to inverse relationships at all. They go intuitively to directly proportional stuff. We're much better at that. But that's part of why we train our brains to do this kind of stuff. So the least amount of resistance is going to be case C. So that'll give us the greatest amount of current pulled from that battery, followed by B, and finally A. All right, next example or next exercise. This one's pretty cool. Focuses on potential difference, which I think is important. And what I always say here is, highlight. Whenever you're looking at potential difference, use your highlighters and color stuff in. So what I'll do is I'll use a red highlighter for the positive side of the battery, and I'll just go in all 4 cases here and highlight. everything that I know is up at that potential, we can call that up at E. Then I'll choose a different color, and I'll go to the low side of the battery, which we can call 0. And then we can pause and look and see what we have here. So yeah, let's look first at case A. So case A, you can see, is basically the case of an open switch. This throws students, but I think it is incredibly important to look at switches because that is how most circuits are made. There's no real point in having a circuit if it doesn't do anything. So remember, circuits are energy distribution systems. In order for them to have any kind of usefulness, they have to have complexity, and we do that with switches. So if I look at case A, that's the case of an open switch. A potential difference is still held by the battery, regardless of whether or not I'm drawing current through that battery. It holds a potential difference. It holds a potential difference if I'm just like, if it's just sitting on a table, if I'm holding it in my hand, right? That's the job of a battery. So I know that the potential difference is there. What's not there, though, and what's not present in this circuit is current. And this is another reason that potential difference is so much more important to focus on than current. Is if you look at this circuit, you could say, well, nothing's going on in this circuit because there's no current. And that's absolutely not true. This circuit, in case A here, has an architecture. And in order to understand that architecture, we have to understand potential. And that way we can know what's going to happen, say, if that switch were closed. Now, having that switch closed is case D. So if you look at case D over here, that's the case of the switch being closed. And I do have a potential difference across this bulb, right? So the potential difference in case D is going to be E, the battery potential. Clearly goes from blue to red, right? But what this is asking us here is the potential difference between these points N and M. So N is on blue, so let's focus on that. N is on blue, M is on red, so that'll also be E, same as the bulb. If I look at case C, N is blue, M is red, that's also going to measure E if I have a voltmeter there. So generally what throws students here is looking at these other cases. Now, since this bulb is not going to be dissipating with the switch open, the bulb is not going to be dissipating with the switch open. There's no potential difference across that bulb. I'm going to paint both of these bulbs through with blue. And then you can see what the answer is here, that in all cases, the voltmeter is going to measure E. It's going to measure the potential difference of the battery in all 4 cases. Okay, so would be all equal and would all equal E. So in a lot of these ranking tasks, they just ask you to rank, but I would say, like, get as much as you can out of these by actually expressing the potential difference that you would measure in every case. Call all the resistors R and just call the batteries E, right? And figure that out, because you have the tools to do that. So we'll go through again with the highlighter here. Again, I'm going to use blue for the negative side of the battery. And I'm going to use red for the positive side of the battery. And let's kind of keep going through here. And if you look at N and M in this case as well here, I still go from blue to red, right? I'm going from blue to red in every case. So in every case, I'm going to measure E. They're all equal again. So now in these cases, ABC, the bulbs are lit up, right? Bulb A is going to be the brightest. It has E across it. Case B, those bulbs are going to be half as bright. They each have E over 2 across them. In case C, they each have E over 3 across them. They're not asking that. I'm just throwing that out there. All right, this last case here, they're wanting us to figure out potential difference from points N to M. And now I want you to think about this, right? These batteries are all identical. Let's call all the batteries are E. The resistors are all identical, and they all are going to have the exact same current going through them. So each resistor, each bulb is going to have a drop of E over 3 across it. So N to M is going to be equal in all cases, right? So all equal, again, I didn't leave myself a whole lot of room there. They're all equal, and they all, all right, let me write this better. Potential difference between N and M is equal to, sorry, E over 3 in all cases. For this one, E over 3 for each bulb. Okay. Moving on, more potential difference stuff. Cool. So again, we're looking at potential difference between points N and M, right? So again, focus on this, and you can use highlighting as appropriate here. So I'll just model that for you. It's an incredibly good technique. And I'll go blue here. All right. So if we're looking at N and M, you can use, if you want to, you can pull different colors and know that you can call, okay, this one here is going to be green. Then I could use 2 different colors in between. I wouldn't use green. I would need to switch colors out because they're different elevations, right? You're thinking about these as elevations. I don't know, purple. There. Okay. So if I was going to do the highlighting, that's kind of what it would look like. So this first case here, what am I going to measure between N and M? I'm just going to measure E because I have the whole battery potential there. Here, I'm going to measure E over 2 because I'm just going, N and M is going over one of the bulbs. I know the drops of both those bulbs have to be equal to E, and I know they're going to be equal to each other because the resistors are the same. And here, E over 3, I'm just going to drop 1/3 of the way. As I want any one of those bulbs will drop 1/3 of the way there. So greatest potential difference there is A, followed by B, followed by C. We'll do the same thing here with the highlighting. I'm going to stick with using red and blue for my battery. So blue for the low side of the battery. You can see where we're going here. Red for the high side. There we go. So in all those cases they're all going to be equal, and then they're all going to be equal to E. I'm going to measure E in all those cases. All right. Now this starts getting a little bit more fun here with this case. So what I want you to notice here is that the difference between M and N, right? The focus is on this one bulb that's wired in series with the battery, right? In every case here, the circuits are different, but notice that that bulb is always wired in series with the battery. So we want to rank where we're going to have the greatest drop over this bulb. So the way I can know that is the drop over that bulb is going to be equal to the current through that bulb, which is actually the battery current, right? So I can call this MN. The battery current, which is through that bulb, multiplied by the resistor of the bulb, which we're just calling R. So really what this is about, since the resistors are the same in all 3 cases, it's about ranking the battery current. And we can rank the battery current inversely with the resistance, with the equivalent resistance. So I know I can do that, C, B, A. My equivalent resistance for case C is going to be less than case B, and that will be less than case A. You can calculate those out. I know, though, when I add resistors in parallel that the overall resistance decreases. Exercise 4. Again, we're looking, I think I'll highlight this one again just to be super clear here. Okay. So yeah, hopefully you're starting to get a feeling for this here. So for case A here, M and N, I can see that's just going to be E. That's going to be the full EMF for the battery. Case B, again, I'm going red to blue, so that's the full EMF for the battery. case C, I'm going from the low side of the battery and I'm going up halfway. This point M here is going to be halfway between the blue and the red. So this is going to measure me E/2. So you could color that area in with, I think I had to use green before to be that elevation there. So in this case, A and B are equal and they're both greater than case C. Okay, equivalent resistance here. This should be feeling fairly comfortable for you now. You've had a lot of experience with equivalent resistance. So we can go through these real quick. We would just have 3R here, 2R, R/3. So these you should be able to do in your head. These are identical resistors. So that gives us A, B, and C. Next case here, 3R. C is R/3. B might take you a sort of extra moment to do. Write it out if you're still feeling like you need a little bit of work on these. This is just going to be equal to 3/2 R. A way you can think about it is you're adding, like you can combine these two into R/2, and then you'd add those in series with R. So that'll give you 1.5 R. So this is again going to go A, B, C. Here we have 2R. They're seeing if they can fool you by moving the resistors around. R/2 and 2R. So A and C are equal and they're both greater than B. And then this one here, as far as equivalent resistance goes, now this is the resistance that's experienced by the battery, right? So you kind of got to consider what is the battery experiencing here. If a resistor isn't dissipating, then the battery doesn't care about it. So if it helps you, you've seen this before, but if it helps you, highlight here the negative side of the battery. So what this shows me here is that, for instance, these two bulbs here are not dissipating. There's no potential difference across them. And these two bulbs are not dissipating. And then I need a third color for the middle case. Again, you've seen this before. Need a third color for the middle case. So in essence, with that wire, just the wire with no components on, sometimes people refer to that as shorting. I don't like that because it's sort of a garage way of talking. It's not really useful. There's no information there. What the role of that wire is, or any conductor, is to bring two parts of the circuit to the same potential difference. So notice if your brain is like, oh, that wire is connecting current, push that away. Try not to focus on current. Every time you're focused on current, ask yourself, should I be focused on potential instead? So when I see the shorting wire, instead of thinking about current at all, or this kind of super simplified notion of like, oh, well, current's just going to take the path of least resistance, that will get you into so much trouble with circuits. It's not, we need to have a more sophisticated understanding of circuits. So, and that sophisticated understanding is using potential to understand them. So when you see this wire that connects, and I'm talking about like saying case A, this wire right here, what that wire does, it acts as a little bridge there to bring the two sides of the circuit. Let me grab a red pen for just a second so I'm really clear on what I'm talking about. This point and this point, those two conductors that it touches, the role of that wire is to bring them to the same potential. That's what conductors will do. So that's how I know I can paint both sides of that blue. Same thing with the green over here. It brings this point, that extra wire brings this point and this point in case B to the same potential, makes them both green just by contact. That's what we do. In case C, the middle wire brings these 2 points to the same, both up to red, both up to E. Okay, so if that is still a mystery to you, that's back in like the Gaussian chapter where we looked at conductors and what happens when conductors come together. So, or, just request an office hour, schedule an office hour, and we can discuss more about that. But it's a really, really important concept. Okay, back to what they're asking though, is they're asking for equivalent resistance, which essentially is what is the resistance that's experienced by the battery. So in case A here, the battery is experiencing a resistance R, right? Just that single resistor. In case B, it's experiencing a resistance of 2R. Both those bulbs are dissipating. They each drop E over 2. In case C, again, just one bulb's dissipating. With E across it, it's true. But the resistance experienced by the battery then is just R. So B has the greatest equivalent resistance, and then A and C are less and equal to one another. All right, back to looking at circuits in this kind of diagramming. This is the type of diagramming that we'll use for the most part. We just want to look at voltage drop here, potential difference. So resistors in the circuit are identical. They give us a value. We can just call them R. The batteries are ideal, 6 or 12 volts. And we are wanting to rank the potential difference from A to ground, or from the upper right-hand corner to ground. So in all those cases, what we're interested in is the potential difference between the upper right-hand corner and the lower left-hand corner. So it would be like attaching a voltmeter to those 2 points. You can kind of think about doing that. Attaching a voltmeter to these 2 points. And something you can always do with these ranking tasks, if any of them really get to you, just build them up in the circuit simulation, right? They'll take not very long. These are all simple circuits. Build them up in the circuit simulation. You can throw the values that they give you onto them, come up with values of the same proportion in order to get the same result. And maybe that'll help to answer some of your questions. Okay, so A and B here, a way that, let's think about how to do this. Maybe I'll stay numeric for this just so that we can talk about it that way. That seems okay. The voltage drop over this. So I'm looking at case A, the voltage drop over each of these resistors. These are identical resistors. So I know over each of these resistors, the drop's going to be 4 volts, right? Because they're identical and they have to sum to 12. 4 is the number that's going to do that. So if I look at the difference between ground and A, I know as I'm going to walk from ground through this battery, right? So I go up 12 volts and then I go down 4 volts. So that's going to give me a result of 8 volts potential difference. I'll do the same thing in case B. I go up 6 volts and that's all I do actually. So I'm still up at 6 volts there. Case C, I go up 12 volts and I don't cross anything else. So I'm still at 12 volts for my potential difference. Case D, I have these 2 resistors, 6 volts at the battery. So I know each resistor is going to drop 3 volts. They have to be identical. They have to sum to 6. I go up through my 6 volt battery and then I drop down through 3 volts at that resistor. So I'm going to measure a potential difference of 3 volts there. These are each going to drop 6. I go up 12, down 6. So I will be at 6 volts at that point. Case F, these are each going to drop 2. Again, identical and summing to 6. So I'll go up 6, down 2. I'm at 4 volts there. All right, so the greatest value is going to be case C. That'll be followed by case A with 8 volts. Cases B and E are equal with 6 volts. Case F is 4 volts, then case D at 3 volts. That is the end of our tutorial.